Hi, I'm Scott Lowe with ActualTech Media, and we're here for part 2 of a discussion with Andy Watson from WekaIO, who is the Chief Technology Officer. We have started to talk about the architecture of the solution, and we're going to go a little deeper now. We're going to start by talking about sort of what happens at the client. The WekaIO client is sort of an interesting thing. One of the things you mentioned was applications don't need to be modified. They all of a sudden just get access to this back-end storage that's insanely fast. Tell me a little bit more about that, especially in the context of a GPU and how it's going to be pumping data over these sorts of systems.
Well, sure. I think the thing to emphasize is that our client is a very lightweight, small piece of software that's running in user space. It doesn't impose a significant, if hardly any, noticeable overhead on the application server. Now, it's there and it looks like a local file system, right? So the application doesn't have to be changed at all. For all intents and purposes, it's reading and writing local files.
So this could accelerate some of those applications that have high velocity data, but it could also be an accelerant for other sorts of general purpose use cases, right?
Mm-hmm. Yeah, in fact, it can accelerate anything. But the crying need that exists in the marketplace today, that the pain point that seems to be the highest profile and that has attracted us the most, because we have limited resources, we're still a relatively young company, is to focus on what we can do to accelerate machine learning, where they have huge amounts of data that's growing daily.
And that's where the GPU
And they use GPUs, and the GPUs tend to experience I/O starvation in that they can run very fast, and running very fast, they can't get enough I/O to keep busy, especially you have 1 GPU in a server, 2 GPUs, 4, 8, right? And that's a lot of I/O, whereas that one server, before it had any GPUs, could be served by something like NFS at 1 to 1.5 gigabytes per second. Now it needs way more. It needs 3 to 6 gigabytes per second per GPU. We can do that, whereas the old approach didn't work. So they bring us in for that, and then you ask, well, what about other general purpose needs? Well, they didn't think of asking us for that, but once they have it in their environment, sure, they use us for anything and everything.
So if GPUs are starved, are there any other potential bottleneck points of a bottleneck in the system architecture between the network and the GPU that would limit WekaIO potentially?
Well, it's not a limit to us, but there is another kind of bottleneck. It's a workflow bottleneck that many of these organizations experience, which is the fact that they have, let's say for genomics analytics, where they have a need to adapt, like a big pharmaceutical company is looking to make their medication more specific to your needs that might be different than my needs. Mm-hmm. And so they'll look at your genome, they'll look at your DNA and my DNA, and they'll try to figure out how to make it biometrically specific. Right? So as they're doing this across large populations, they have huge data lakes of genomic data. Right? So one of the things that slows them down is getting the data out of the data lake and feeding it into the applications that they're running to perform their analytics. Now, before they knew about WekaIO, they would at least consider doing something like pulling the data out of the data lake and making a local copy. Now, running off a local copy, sitting on SSD on the local host, that seems fast, doesn't it?
To a point, but there's going to be some limitations there too.
Oh yeah, big time. We're actually faster than that local storage because we're giving them access to more parallelism across more resources. And furthermore, what about the wall clock time of pulling all that data together, organizing it, and copying it? If you add that, right, now you're doing 2 things. You're doing the actual I/O against the data, and you have to do the copy of the data. There's more I/O associated with the task. So if you put all that together, we're not just a little bit faster, we're much faster than doing local copies of the data for your analytics tasks. So the very nature of having many petabytes growing to exabytes of data in a data set for a particular analytical task drives you to need a solution like what we offer, where instead you can put the data out on, in parallel, large amounts of flash storage that has access to this effectively nearly infinite quantity of hard disk-based object storage that we can manage for you transparently, so that these applications don't have to go through this workflow-based approach to copying data before they even run any task.
One of the things that's been interesting over the years is if we watch solutions address one piece of the I/O stack, there's been second-order consequences. For example, RAM all of a sudden becomes a bottleneck, or we see CPU become a bottleneck. Does moving storage to something so massively scalable and parallel result in identifying or uncovering other bottlenecks that exist somewhere in the architecture that are not managed by storage?
Well, I think inevitably it's Whac-A-Mole, right?
Yeah,
so
that's exactly what I'm trying to get at.
Right. So you speed up the CPUs, now you're waiting on I/O. You speed up the I/O, now you're waiting on storage. You speed up the storage, oh, now you're back to waiting on the CPU. So of course you want all of your resources to be in balance, right? And that's always true. So if we come in to an environment and we make the storage much, much faster, that may indeed identify other areas that they can now invest in improving. But that's a little bit like a fingerprint. Every environment's a little bit different, and depending on what kind of applications they're running, what their workflow looks like, they may need to invest more in their networking, they may need to invest more in their CPU and GPU resources.
One of the things you mentioned in part one was that the solution is bypassing local scheduling mechanisms to be able to maximize throughput and I/O and all that stuff. Is that happening just back here, or are you doing it over here with the WekaIO client as well?
We do it a little bit with the WekaIO client.
That's probably a little harder, I would imagine.
Well, in the step where we're going to the network, right, we do bypass the kernel to go directly to the network interface. So that part, right, we take advantage of because we're running on user space.
Is this a dedicated network then for just this solution?
It doesn't have to be, but there are benefits to isolating your network traffic. It depends on what else you're using the network for.
Right.
Our software, by the way, the same exact executable binary runs on AWS, and people, in fact, typically do a POC test in AWS before they deploy on-prem, and they know that, well, on AWS, you've only got 25 gigabits per second, not 100,
right.
And it's a shared network, not a dedicated network, so they know it'll only be better when they go on-prem. So it's the same story on-prem. Should be a dedicated network for the best possible outcome. Doesn't have to be.
So I didn't mean to interrupt you about the scheduling piece, but keep going on that.
Yeah,
That's interesting.
So we do have our own mechanism for going directly around the kernel and directly to the network interface card so that we can get data on and off the network without waiting for the kernel interrupt. So we get much lower latency I/O on the application servers using the WekaIO client. The same, of course, is happening, I think, as I explained on part one, when we go to and from the SSD. I think that's the wrong place to draw it. But anyway, over here on the SSD and to and from the network on the card there. We're always doing things in user space, outside the kernel, not depending on the kernel for drivers, and trying to optimize the data path so that there are no interrupts. And every data I/O event runs to completion without interrupt.
So the question I have on the bypassing interrupts, particularly on network, does that impact other applications that might be on that server as well if they are using the scheduling mechanism, or is this just for CPU scheduling an event to the network and it's not impacting how the network is being treated at all? So
we reserve cores here on these systems. If you were using these systems, because these are just x86-based servers, you might want to use the hardware for something else in addition. So we have some customers who use them dedicated only for WekaIO storage nodes, but you could run stuff on them, and we call that converged mode. In fact, you could be running application servers on the same systems that are running as storage nodes, in which case you could have contention for physical resources, except that we reserve cores. So those cores now are just dedicated to running our software, and the contention really doesn't exist at that point.
Got it, right. And that's how, another way you get past the scheduling issue, because you're going to reserve those cores.
Of course.
Got it.
Yeah.
Cool. So what else should we know?
Oh, well, what else could I tell you? We've covered a lot of ground today. One of the things that I happen to like a lot about our solution that is not necessarily so much architectural as a feature, but it's a really cool feature, is that we're able to take snapshots. So we have up to 4,096 snapshots per file system, and we can have 1,020 file system abstractions per cluster. Now, each file system has the entire physical resources of the cluster at its disposal. So unlike other implementations from other vendors, when you have two file systems, normally you're splitting your resources. In our case, no. Every file system has all the resources, so they're all equally fast, and it's one of the ways to do multi-tenancy in our case. So now, each file system can have all these snapshots going on the same way you use snapshots in other systems. We have a special kind of snapshot in addition to that called snap to object. That would take a snapshot, including all the metadata for all of the files, including the files that are out here and all the live files that are still only in Flash. And this snap to object object, right, will be written out here, and now we have this snap to object here, and it itself could then be moved somewhere else. Now let's say it's over here on another object store, right? Not the one that's associated with our file system. This snap to object could then be wholly or partially rehydrated, right? Individual files, directories, whatever portion of it you want, into another WekaIO cluster of whatever size. It doesn't have to have the same original geometry. This one might be a very large cluster. This might be a very small one. So for example, suppose this was AWS S3 and you put the snap to object up here into S3, you could create a small, maybe a dozen nodes that you start up in you start up in Amazon on AWS, and you point it at the snap to object and you rehydrate from the snap to object, you rehydrate a subset of the data. Why? Because you want to do cloud bursting. Now you cloud burst against it, you do some processing, now you do a new snap to object, capturing your delta, your changes,
right,
and you bring that back. So basically it's bidirectional. So you can do this for DR,
right,
and you can do it for cloud bursting.
Wow. So there's some pretty cool stuff going on under the hood on this thing.
Oh yeah, oh yeah.
Andy, thank you so much for this great overview of the WekaIO solution.
I really appreciate you taking the time. Thank you very much.
And thank you to our audience for watching this video.